Hello, and welcome to a journey beyond our solar system. Every few years, a traveler from another star system crosses our cosmic backyard. These interstellar objects, like the recent visitor 3IATLAS, raise a fascinating question. Could one ever be caught, pulled into a permanent orbit around our Sun? For an object to be captured, it needs to slow down significantly. Think of it like trying to catch a baseball thrown at lightning speed. You can't just stick your glove out. You have to move with it and absorb its energy. For a space rock, this means losing what's called its hyperbolic excess velocity. This can happen in two ways: a complex gravitational dance with giants like Jupiter, or by acting like a rocket, venting gas in the opposite direction of its travel, especially as it warms up near the Sun. Simulations of 3IATLAS, which blazed through at a staggering 32 kilometers per second, showed it would need to shed at least 3 kilometers per second of its speed to get caught. That's a huge energy loss, far more than what could realistically be achieved by outgassing. So, 3IATLAS was just a fleeting visitor. However, the story doesn't end there. The models suggest that a slower interstellar object, one traveling at less than 10 kilometers per second, could be temporarily captured. It might get nudged into an orbit resembling one of Jupiter's comets, circling our Sun for tens of thousands of years before eventually being flung back out into the void. What's truly mind-boggling is that statistically, one such captured wanderer might already be orbiting the Sun, hiding in plain sight, a silent relic from another star. Now, while capturing an interstellar object is a captivating idea, their high speed also poses a serious threat. This is where planetary defense comes in. The energy of an impact is determined by mass and velocity, squared. Because interstellar objects approach us at incredible speeds, between 30 and 60 kilometers per second, they pack an extraordinary punch. A relatively small 100-meter wide object, if it were to hit Earth, could release energy equivalent to 10,000 Hiroshima bombs. This makes early detection absolutely critical. We're not defenseless, though. The Vera C. Rubin Observatory is set to become our first line of defense, scanning the skies for these fast-moving threats. It will be complemented by NASA's NEO Surveyor, an infrared telescope that can spot dark, non-reflective objects that are invisible to optical telescopes. These systems are being linked together under NASA's Planetary Defense Coordination Office, using machine learning to instantly flag any object on a high-velocity trajectory that hints at an interstellar origin. This network will give us the precious time we need to react. Beyond the potential danger, these interstellar visitors could be carrying the most profound cargo imaginable, the building blocks of life. The idea that solid material can be exchanged between star systems opens the door to a concept called lithopanspermia, the transfer of life, or the chemical precursors to life, across space. If comets like 3IATLAS formed in water-rich, organic-laden environments, they could act as galactic couriers, spreading the seeds of carbon chemistry throughout the Milky Way. Laboratory experiments have shown that amino acids, fundamental components of life, can survive the violent shockwaves and intense heat of being blasted off a planet and crashing into another. Furthermore, models show that microbes, sheltered just a couple of meters beneath the icy surface of a comet, could survive the harsh radiation of interstellar space for millions of years. This transforms our view of these objects. They aren't just cosmic debris, each one is a potential molecular envoy, a message in a bottle from one biosphere to another. What's truly remarkable is what the composition of 3IATLAS tells us about the universe. When we analyzed its chemical makeup, we found that its molecular and isotopic patterns were surprisingly similar to comets from our own solar system. This supports a beautiful hypothesis called chemical homology. The idea that the basic laws of chemistry and physics lead to similar outcomes everywhere. The ratios of different volatile materials like carbon monoxide to water seem to follow universal rules based on their binding energies and the heat from their parent star. This means that across light years of empty space, the fundamental chemistry that forms planets and comets converges. It's evidence that physics, not random chance, dictates the cosmic recipe. This chemical consistency greatly strengthens the argument that life might be a common phenomenon, likely to arise wherever the right ingredients, liquid water, organics, and an energy source, are found. This exchange of material has led astrophysicists to a new model of our galaxy, a galactic conveyor belt. Imagine that for every star like our Sun, hundreds of millions of icy bodies are ejected during the chaotic formation of its planetary system. Over billions of years, these cosmic travelers fill the space between stars. Each time one of these objects passes through a planetary system, it's like a cosmic reshuffling of the deck. Material gets exchanged, and some of it is thrown back out to continue its journey. It's a slow, galaxy-wide diffusion process. Through this mechanism, atoms of carbon from one star could one day become part of the biology on a planet orbiting another star, countless light years away. In this sense, the Milky Way isn't just a collection of isolated stars, it's a living network, constantly exchanging matter and information through these cometary messengers. Naturally, the next step is to go out and meet one of these travelers. The European Space Agency's Comet Interceptor mission is designed to do just that. It will be parked at a stable point between the Earth and the Sun, waiting. When a new interstellar object is detected on a favorable path, the spacecraft can be dispatched within weeks to perform a high-speed flyby. But that's just the beginning. Future concepts, like NASA's Interstellar Probe or projects inspired by Breakthrough Starshot, are exploring miniaturized spacecraft that could achieve incredible speeds, fast enough to catch up with and study these objects up close. These missions would allow for direct sampling of their material, giving us an unprecedented look into their composition and origin. It would be a monumental leap, transforming our study of interstellar objects from remote observation into hands-on laboratory science. As we catalogue more and more of these visitors, we'll usher in a whole new field of science, exosystem geochemistry. By analyzing the spectral signatures from countless interstellar grains, we'll be able to create a chemical map of the Milky Way. We could trace gradients of different elements and molecules across the galaxy, connecting the evolution of stars with the chemistry of planets in a single, unified story. And in that story, 3IATLAS will be remembered as a milestone, the object that helped turn a rare curiosity into a predictive science. Ultimately, beyond all the data and equations, these interstellar visitors offer a profound philosophical insight. They show us a universe without rigid borders. Fragments of one world journey to another, molecules outlive their parent stars, and atoms from long-dead planets can be reassembled into new oceans and perhaps new life. 3IATLAS, in its brief passage through our sky, reminded us that the cosmos is not a collection of isolated islands, but a single, interconnected ocean of matter and memory. Its journey is a testament to the fact that the story of any one world can never truly be written alone. Thank you so much for joining me on this exploration of the cosmos. If you enjoyed this journey, please consider liking this video and subscribing to the channel for more deep dives into the wonders of our universe. See you next time.